Right, and so the last talk before we have a little panel session is kind of a double act, but it's a change. So it's from the Sanger Institute. It was going to be James Beal and Dave Holland, but Dave Holland's not around. So Rich Mansfield is pretending to be Dave Holland. he will put on the access. But anyway, thank you. Who ain't my IOPS? Identifying heavy hitters using job stats. Take it away, guys.
I'm James Beal. I'm from the Wellcome Sanger Institute. This is Dave.
I'm Dave from 2.0.
We do sequencing. Pictures of some sequences. They produce lots of data. We have about 20 of our main sequences. Slide that says price of sequencing is going down, price of compute is not going down. It's not good. Right, what do I want? I want a pony. Nobody ever gets me a pony. The problem statement is we have file systems. The issue is when people are using it, it goes slower for other people. One user is used to 1.5 gigabytes per second. When the file system is contended, they get 100 gigabytes per second. They're grumpy. It'd be nice for us to know who was using the file system. We have loads of file systems. The ones in yellow are disappearing, grey ones are new. We have about 25,000 of batch scheduling cores. We have about 20,000 cores in OpenStack. Job stats. Job stats are a method of tagging I/O. They've been around for a long time. We haven't seen much use of them, or haven't seen any presentations on how they can be used. I think I hand this over to you now.
Okay, well, thank you very much. So I think everybody probably in here will recognise a situation where people, users come along and say, hey, Lustre is slow at 12 o'clock yesterday, so how can we handle this? And a file system is a resource, because any resource you have to manage. If you don't manage that resource, you have no knowledge of what's going on below the scenes. So, in sympathy with the work which Sanger are doing, is trying to find those jobs which either aren't performed because of reasons you need to look into, or aren't performed because something else is happening on the system, and it's finding that other thing is important. So if you find that thing which is actually slowing the system down, at least you have the ability to do some preventative actions, so remedial action, for example. So job stats is a method to allow you to actually look under the covers of what's happening across all of your computer nodes at the same time. Problem is, as James was saying, it's a probably underused facility. I think more people should be familiar with its functionality out there. But if you're familiar with the standard method of Lustre stats, you basically get some OST or some MDT stats, and they have this beautiful output from the command line. So this is not really human consumable, because it's just a lot of numbers. But it's a very, very similar thing. So you have your operations down the side. These can be OSS, they can be some bulk data, could be metadata data. They have some metrics on the side. There's standard min, max, sum, and some squared, which kind of measures the deviation between your averages. But this, in its entirety, is not very helpful. This is supposed to be a YAML file, and it's one thing which James and his team quickly found, that it's hard to parse this because it doesn't strictly adhere to the YAML directive. So there's some things in here which aren't right. First off, you specify this command on the command line, you get some output, and you got this stats which appear. Now you have to firstly ignore the first two lines in red, because that basically breaks your code. The job ID will come back to that. Hopefully, James, you talk about the better stuff. The
comment here is that it's not got any quotes.
Yes. Yeah. So, and then the other comment is that these text fields can be overrode, so overwrite the fixed field. So if this number in particular gets too big, then you have a problem where you can actually you have to manipulate this and work around that code. Anyway. But if you did have that, like anything with statistics, you select this by some method, and you can export it to your standard Grafana or whatever Prometheus monitor tool which you're out there. However, so what we're trying to do here, so the good thing which James' team has done is using all this job stats to embed some key metrics inside every RPC. Users, groups, the job ID, and additional to that, so extra richness, extra goodness. So it's like LSF, they have a project ID associated with every job out there. So these are the additional fields we want to put into the code, so that if we can then look at, this is a standard kind of output of time series database with reads and writes, is what you probably normally expect, but now I want to dive deep under the covers to look at a user or a group or a response to a particular project ID. So we'll tell you how we do that at the moment, but let's just kind of see what we have done for the moment. So multiple file systems, yes, we select our file system. This is an interesting bit here. This shows you how we want to slice and dice information on the screen. So you may be interested to find out which compute form is being overrun, which user's taken a particular amount of data, which group is running your IOs, which, and probably more importantly, what project ID, what job ID is actually being run at the same time. So you can select those two, which is normal kind of richness, and specify over timeline. So this will show here that we have like whatever 2 days worth of output. This is the peak here. This is what we need to look at. So imagine this situation where somebody says, at that particular time, something's going on. What was going on at that time? So this graph looked probably pretty much similar to what was happening yesterday, but a user swears blind that my code at that time was going wrong. So now, because we got job sets enabled, we can zoom in at that particular time and have a look at what's running. So in addition to the normal metrics, bandwidth, IOPS, bandwidth, IOPS, and metadata, metrics, there's a human element on here, or some human interactions. They demand resources of the file system. So what we can actually do with job stats is look at that peak and zoom in to find out at that time what was running. So we can first of all identify who's running that job, taking the most consumed amount of bandwidth, 52 gigabytes per second at that time, and any arbitrary point in the past. And this here is basically what's happening now. Now, because we can look what's happening below the covers, and it's not just the 10,000-foot view of a response to a file system running a job yesterday, which looked like this, and yesterday it looked like this. It looks exactly the same, and now you can actually see what's actually jobs are running at that particular time. Likewise, that's one way to slice and dice down to a user, but in Sanger's particular case, they are also very interested in what's the project. Every scientific group has sort of projects, and you want to then look at which group, which project is running at the same time. So you also look at the teams. So this is another way to actually look at the outputs. So now we can look. So that's one way to look at the problem. So you have established pipelines of code. Users run it all at the same time. We can actually identify, in this particular case, malpipe is actually a service account. So it's not a user. It doesn't resolve to a particular name or group ID, but it's a user on the system, a service account. Unfortunately, there's some applications out there in life science which takes your environment variables, their applications are kind of pre-packaged, it literally destroys all of your environment variables. So this uses, I'll show you next way, that information is pulled out of environment variable set at runtime. So some pipelines amazingly destroy all of that, so quotes, clean up your operations. But in doing so, by cleaning up all your environment variables, you get a situation where you have an unknown situation. So you can't, so this is certainly a feature which we, as in James, has to talk to some of these pipelines constructed by commercial companies and not unset some environment variables. So that's one way. This is the new way which Sanger will be looking at, having to taking a user to find that user of highest consumed bandwidth IOPS and metadata, and mix that with the more traditional method, whereas before. So this is where we got the Lustre, up here, the Lustre per user stats. We find out what's happening at that particular time. We could then also look back to the more traditional method of monitoring the system in terms of OST usage, MD usage, and from here we can actually use one way. So from a user going through to the system, or for this case, look at the system statistics going back into what's happening to the user. And sure enough, for this particular file system, we can see this is more traditional method that every OST is nicely used. You've got large files or taking advantage of striking mechanisms. So now we've got both ways. We can do a very low level per user or a very high level at the file system level. So James, do you want to show the magic code?
First thing to say is there's very little code. There's 80 lines of code on the Lustre server, and 25% of that is the license. The code on the monitoring node is about 180 lines. So this is all very simple. Keep it simple. Right, so user submits a job. Our LSF system embeds an environment variable, 2 environment variables, one that will get past singularity and one for normal operations. Job gets scheduled, eventually it will be run. The environment will be copied by LSF. Compute node will do I/O. I/O client, Lustre client embeds the job stat given the environment variable if it's set. If not, you get just the default. I/O happens. Monitoring node every 3 minutes talks to a little HTTP server on each of the Lustre servers, does the aggregation, sends to Graphite. User looks at Grafana, drafts some happiness. Right, there is some code. Top one, just going to say each get we see what OSSs and MDTs are around, and that means we're resilient to failover. 2, there's some issues in the YAML. We have to work around it. 3, encode the data. It's worth pointing out we do base 64 encoding, so we don't use 18 bytes for the 3 16-bit numbers we want. So we actually have some spare space. Output, you can do a curl, you get enriched data. Pretty pictures. There's a reason I didn't do that bit of the talk. I say pretty pictures, you can see what they do. Bugs are pain. Can we get the YAML to be correct? LU1610 is annoying. This here, we shouldn't get. This bit is one job stat. This bit is another job stat. You've just tried to write it to the same place. That's not good. You've got a bug. It's a race condition. There is a bug. You're working on it. It looks like it's a patch. C code. I'm not. Right. Secure Lustre. I'm going to be over in 3 seconds. Secure Lustre. The job ID is inserted on the client. That means that on the client, most of our users are 1,000. The UID is inserted on the client, means that I get 1,000 on the server. Could you give us the node map that the I/O came in on? Would be nice. So currently our current system, because it comes in as really not a valid user, means that it currently gets dropped. That's something I can fix. Small change on the Lustre server, tiny little program. It's not perfect, it's usable, it's tiny. And for the future, what would I like? I want fair share for my I/O, and I am done. Or nearly. I want to say thank you to everybody in the group I'm in. Thank you to Dave. Thank you for the real Dave, and thank you to my proxy Dave, and I am done.